Hello friends, my name is Tushar and today we're going to talk about how to do deletion in red-black tree. In another video, I gave introduction to red-black tree and how to do insertion in red-black tree. In this video, we are just going to talk about how to do deletion in red-black tree. So to delete a node in a red-black tree, first we have to find a node in a red-black tree, and red-black tree is a binary search tree, so we have to do a binary search to find that node. Once we have found that node, then we check if it has two not null children. If it has two not null children, then we have to convert into a case where it has 0 or 1 not null children. After doing that conversion, we check if the node to be deleted is red or if its child is red, then it's a very simple use case. Otherwise, we have a double black use case, in which case we will have 6 different cases. So let's try to understand this entire process with the help of examples. Here I have a red-black tree. And as you can see, the leaf nodes are pointing to null nodes. Null nodes do not store any information except for the fact that they are black nodes. So while during insertion, when you create a leaf node, instead of leaf nodes pointing to null, they should point to a null node. So let's make sure that this is a red-black tree. The root is black, there is no red-red parent-child relationship, and the count of black nodes in every path is 3. So this is 3, this is 3, this is 3, this is 3, and so on. So the thing with insertion was we were inserting a red leaf node, and if that red-red relationship was created, we were doing some rotations and other things to fix that red-red relationship. The thing with deletion is that we might delete a black node which will decrease a count of a black node in that path, and to fix that we'll have to do some rotations or some other techniques. So let's try to delete 30 in this example here. So I'm trying to delete node 30. So we start from 10, 30 is greater than 10, so we go on the right side. So we found 30. So now 30 has two not null leaf nodes. So as we discussed, we have to first convert into 1 or 0 not null leaf node. To do that, we find the in-order successor of 30. So since it has a right child, the in-order successor of 30 will be on the smallest node in the right subtree of 30. So the smallest node on the right subtree of 30 will be 38, and then go as left as possible, so which is 35. So what we do is we replace this 35 here. So this becomes 35. So we deleted 30, but we end up having two 35s. So then what you have to do is, in this subtree here, you have to delete 35. So we go from 38 to 30, we go to 38, 35 is less than 38, so we come to this point. And now 35 has two null nodes. And also the color of 35 is red. So to delete 35, all you have to do is just remove it and replace its left child with null, 38's left child with null. And by doing this, you do not affect the red-black tree property because you can safely delete a red node and it does not affect the counts of the black node in any path. So this takes care of our use case. If it's just a red node that needs to be deleted, then we can just delete it. Let's see what happens if a black node needs to be deleted and its child is a red node. So this is a similar tree like last time. The only difference is that the count of black nodes in every path is 4 and not 3. Again, let's try to delete 30. So we start from 10, 30 is greater than 10, so we come to this point and we find 30. Now 30 has two not null nodes. So now we have to convert it into a situation where it is 0 or 1 not null node. So we find the in-order successor of 30, and the in-order successor of 30 is the smallest on the right subtree. So we go to right and then we go as left as possible, which is 32. And then we replace 32 with 30. So this becomes 32. So we took care of 30, but now we have two 32s and we have to take care of this 32 and remove this one. So to remove this 32, we continue our search. So we look for 32 from here. So 32 is less than 38, so we come to this point. Now last time the color of this node was red and we just deleted it, but this time the color of this node is black, but it has one red child, 35. So what we do in this case is delete this 32, replace it with 35 and change the color of this 35 to black. So let me do that quickly. So this becomes 35 and it has two null nodes whose color is black, and change the color of this 35 to be black. So what happened here was we continue to have the count of black nodes as 4 in this path, 1, 2, 3 and 4, and we also ended up deleting 30. So hopefully this helps you understand these three cases. How to convert to a situation where you have 0 or 1 not null nodes. And then we do that by finding the in order successor. And then if the node to be deleted is one red node with two null children, then you can just delete that node as we looked before. And if the node to be deleted is a black node with one red child, then replace that red child with that node and change the color of that red child to be black, as we saw in this use case. Now if we have if we have to delete the node which is black, which has black children, then we have double black use case, and it has 6 different cases, and let's try to understand those cases with the help of examples. Let's first try to understand what double black node means. So let's say I was trying to delete 10 in this red black tree. So I start from root is 10, so we have to delete this 10, but it has 2 not null children, so we have to convert it into a case where it has 0 or 1 not null children. So we look for the in order successor of 10 in the right subtree, which is the smallest element in the right subtree, which is 20. So first we replace 10 with 20 here, so this becomes 20. So now we have taken care of 20, we have taken care of 10, but we have 2 20s in this red black tree and we need to delete this 20. So we go to 30, look for 20, 20 is less than 30, so we come to this point and we found 20. So now if you remember from before, if the color of this node was red, we could have just deleted it, or if it had one red child, then we could have replaced that child with this one and colored that black. But in this case, the color is black and it has 2 black null nodes. So we need to somehow delete this. So the way we do it is we delete this node, replace it with one of its child null nodes. But now the problem is, in every path the count of black nodes is 3, while in this path the count of black nodes is 2, because we deleted one of the black nodes. So this black node here now is a double black node because it is carrying the weight of this extra black node. So double black node indicates that the path going through it is going to have one less black node than the rest of the tree. So now to fix this double black node, we have this 6 different situations. In this, this here is indicating a double black nodes, while purple is indicating that the color of the node could be either black or red, and it does not matter. So next, let's try to understand how these cases work and how we fix a double black node using these cases. When you hit a double black node, you try to apply these cases one by one and then move on to the next case unless the case is a terminal case. So case 1, case 4 and case 6 have asterisks in front of them, meaning that they are terminal state, and when you do the transformation for this case, then you're done and tree is back to be red black tree. Otherwise, if you hit a case 2 and if it does apply, then you do the transformation and then move on to case 3, and if it does not apply, then you still move on to case 3. And similarly for case 3, if it applies, then you do the transformation and move on to case 4, and if it doesn't apply, then you still move on to case 4. Also, other than case 1, all these cases have their mirror images. For example, for case 2 here, the double black node has a red sibling and the parent is black and both the children of the sibling are black. So the mirror for this one would be that the double black node is the right child while the red sibling is the left child, having 2 black nodes and black parent. So all these 5 cases will also have their corresponding mirror cases. So let's try to understand each cases one by one with help of example. Let's start with case 4 because I feel case 4 is simplest of all the cases. So let's say I was trying to delete 20 in this red black tree. So I start from 10, 20 is greater than 10, so we come to 30. 20 is less than 30, so we come to 20 and we found 20. Now this node here is a black node, so by deleting it we are creating a double black node situation. So we delete 20, replace it with one of its null children, But this node here now is a double black node because the count of black node in this path is 2, which is 1 less than rest of the tree. So now we see which case is applicable for this double black node. So this double black node is not the root of this red black tree, so case 1 is not applicable. By the way, these boxes here indicate that there could be subtrees under this double black node. The only thing is that the count of the black node via this double black node will be 1 less than rest of the tree. So going back to this, case 1 is not applicable because this is not root. Case 2 is not applicable because the sibling here is black in color while this sibling is red. Case 3 is not applicable because the parent here is red in color while the case 3's parent needs to be black. Case 4 is applicable. The parent is red, sibling is black, both its children are black in color. So now we do case 4 transformation. So in case 4, all you have to do is exchange the color between parent and its sibling. So this becomes red and this becomes black. And also case 4 is a terminating case. It means that as soon as we do this transformation, we are done. So let's see if we are done or not. So now as soon as we move this black node here, the count of black node in this path increased by 1. So this is not a double black node anymore because the count of black node in this path is back to 3. Also the count of black node in this path did not change because we just moved the black node up and took the red node down. So here we did a case 4 transformation and this tree is back to red black tree. Next, let's look at case 6. Let's say I was trying to delete minus 10 in this red black tree. So minus 10 is less than 10, so we come on the left side, we found minus 10. It is a black node with 2 black null children. So by deleting minus 10, we create a double black node situation. So we delete minus 10, we replace it with one of its children, and we created a double black node situation here because the count of black node in this path is 2 while in every other path is 3. So now let's try to see which case is applicable here. Case 1 is not applicable because this is not root of the tree. Case 2 is not applicable because the sibling is black and not red. Case 3 is not applicable because the children are red and this children are black. Case 4 is not applicable because the parent here is red while the parent here is of double black node is black. Case 5 is not applicable because the right child of the sibling is black while the right child of this sibling is red. So we come to case 6 and case 6 is applicable. The right child of the sibling is red in color, sibling is black in color, the color of the parent and the left sibling does not matter. So in case 6, what we do is we do a left rotation and we do some recoloring. And for its mirror image, we do a right rotation and recoloring. So in this case, we will do a left rotation. So we do a left rotation at this point here. So 30 becomes the new root of my binaries of my red black tree. 10 will become its left child. 40 will continue to be its right child. 25, which was the left child of 30, will now become the right child of 10. And null stays as is. And they have their own null nodes. So after you do this rotation, you also need to do some recoloring. So 30 takes the color of whatever the color of 10 was, which is black. So this becomes black. 10, whatever its color is, doesn't matter. 10 will become black. So this becomes black. 25's color stays same. And 40, which was red in color, will now become black. And these are all null leaf nodes whose colors are black. So before transformation, this was a double black node. Now this is not a double black node anymore. Why? Because we increased the count of black node in this path by 1. So now the count of black node is back to be 3 in every path. So this is 3, this is 3, 3, 3 and 3. So this is why case 6 is also a terminating case. As soon as you hit a case 6 and you do this transformation and recoloring, this tree is back to be red-black tree. So next, let's look at case 5. Let's first look at case 3 before looking at case 5. So in this red-black tree here, I'm trying to delete -10. So -10 is less than 10, so we go on the left side, we found -10. It has 2 null black children, so we delete this node, but it creates a double black node situation here, because the count of black node in this path is 2, while the count of black node in every other path is 3. Now we see which situation applies. So we start from here. This is not the root of my binary of my red-black tree, so case 1 is not applicable. For case 2, the sibling here is black in color, while for case 2 it needs to be red in color, so case 2 is not applicable. Case 3 is applicable. 2 black children, black sibling and black parent. So in case 3, what we do is we just change the color of this to be red. By doing this, what happened was the count of black node in every path starting from this, their parent, is now going to be same. So we reduce the count of black node in this path. So starting from 10, the count of black node in every path is going to be same. So basically we pushed the problem upwards. So now 10 is my new double black node and it needs to somehow fix itself. So after we hit case 3, we again go back from the top and start applying and see which case is applicable. So after we are done doing the case 3 transformation, in which we just change the color of the sibling to be red, we go back. Now this is our new double black node. We go back up again and see which case applies. So now the root of my red-black tree is double black node. So case 1 is applicable. So if case 1 is applicable, you do nothing, because all you did was, so this can safely be converted into a single black node, because it means that you just reduce the count of black node in every path by 1. So now if you see, the count of black node in every path is 2, and this here is a red-black tree. So as you see, case 3, if you do a case 3 transformation, you are pushing the problem upwards, and then you are again going from the top and seeing which case is applicable. Also, you saw an example of case 1 here, and as you can see, case 1 you will never hit a case 1 directly. You will always hit case 1 by case 3 transformation. So you'll first hit case 3, push the problem up, and then you might hit a case 1 situation, as you saw in this case here. Next, let's see how we get a case 5 from case 3. Now let's see a case 3 which results in case 5 situation. So here I'm trying to delete -40 in this red-black tree. I start from 10, -40 is less than 10, -40 is less than -30, and I found -40. -40 is black node with 2 black null children. So we delete -40, but this creates a double black situation. We replace it with one of its null children, but this creates a double black situation here, and now we see which case is applicable. So we start from here. This is not root, so case 1 is not applicable. Case 2 is not applicable because the sibling is black. Case 3 is applicable because sibling is black, has 2 black children, and the parent is black. So as you remember, in case 3, we change the color of this to be red, which means that under this, the count of black nodes is now same. So in this subtree, the count of black nodes is 2, but by doing this, we pushed the problem up. By changing this to red, we push the problem up, and now -30 is my double black node. And somehow we need to fix -30. If you remember from last time, -30 had become a root, so we just did nothing. But in this case, it is not a root. So we, after doing this transformation, we start from the starting. It's not root, so we go to case 2. The sibling is black in color, so this is not applicable. We go to case 3. The sibling's left child is red, while this needs to be black. So case 3 is not applicable. Case 4 is not applicable because the parent is black, while for this parent needs to be red. Case 5 is applicable. The sibling of -30 is 50, is black in color, so this is black. Its left child is right, and right child is black, and the parent is black. So case 5 is applicable. So in case 5, what we do is we do a rotation here and try to convert it into case 6. So all we are going to do is do a rotation here. We do a right rotation, so 10 stays same. Then we do a rotation here, so 30 becomes the new root of this subtree. 50 becomes its right child. 70 stays as its right child. It has null and null. And then 40, which was the right child of 30, becomes the left child of 50. And 15 stays the same, and it has null, 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 and null. So now, after doing this rotation, we have to also do some recoloring, as you can see here. So basically we swap the color of these two. So before this was red in color before transformation, so this becomes black, and before it was black, so this becomes red. So now, and rest of the tree is same. So minus 30 is still my double black node, and it has minus 20 here as a red child, which has null, null, and null. So nulls are obviously black in color, and this is black, and 15 is black, 40 is black, and 70 is also black. So we did a rotation here. We changed the color of 30 from red to black, and color of 50 from black to red. Now we did a case 5 transformation, and it's not a terminal case, so we still have this double black node, but we turned it into a case 6. So after doing case 5, we move on to the next case, and as you can see, case 6 is now totally applicable here. So the sibling is black, it has one red child, and the color of the other child and the parent doesn't matter. So once we do this transformation, after this we need to do one more case 6 transformation. So let's do that quickly. And then this will turn into a red-black tree. So in case 6, what we're going to do is we're going to do a rotation of this entire tree at this point. So 30 becomes my new root, 50 is its child, right child, 70 is its right child, 40, and then 10 becomes the left child of 30, and 15 becomes the right child of 10, and minus 30 stays wherever it was, and minus 20 stays wherever it is. And then they have nulls, which are black in color. So now, in case 6, if you remember, we change the color. So this takes the color of this, and this becomes black. So this was already black, so it stays black. And this takes the color of 10, so it becomes black. And this child also becomes black. So 50 also becomes black. So this becomes black. And the rest of the guys keep their same colors, which is black. And this stays red. So after doing this transformation, you can see the count of black nodes now is same in every path. So in this path it is 4 because all these nulls have black color. So it is 4. In this path it is 4 because this is red in color. In this path it is 4. It is 4, it is 4, and it is 4. So as you can see, we never hit case 5 directly. We'll start with case 3, we bubble the problem up, and it might result in case 5. And once you hit case 5, all you have to do is do one rotation to convert it into case 6. And once you do a case 6 rotation, it converts the tree back into red-black tree. So we started with case 3 followed by case 5, which resulted in case 6, and then the final transformation to convert it back into red-black tree. Finally, let's look at this case 2. Let's say I was deleting this 10 in this red-black tree. So we found 10, it has 2 not-null children, so we need to convert it into a case where it has 0 or 1 not-null children. So we look for the in-order successor of 10 in the right subtree, which is 20. So first we replace 10 with 20, and now we have converted it into a problem where we have to delete this extra 20. So we find this 20. Now this 20 is black, its children are 2 black null nodes, so we have to convert it into a, so we delete 20 and it converts into a double black node. So we replace it with one of its children, which is a double black node now. So now we see which of the condition gets applied. So this is not the root, so case 1 is not applicable. We come here, the sibling of this is red in color, sibling is red, parent is black, both the children are black, so both the children are black. So case 2 is applicable. So in case 2, what we do is we do a rotation. So what that means is we're going to rotate here between this 40 and 60. So 20 still stays the root of my tree. 60 becomes the new root of this subtree. 40 becomes its left child. 80 is its right child. And 50, which was the left child of 60, will become the right child of 40. And null stays wherever it was. And then, after this, the color of 40 and 60 will be exchanged. So 60 will now become black and 40 will now become red. And rest of the tree will stay same. And all of them will have null nodes under them. So after we are done doing this transformation, we still have this double black node. The problem is not yet solved, but we have converted into a problem where the sibling now is black in color. Before transformation, the sibling was red in color. After this transformation, the sibling is black in color. So now we are going to see which other case gets applicable. So case 2, by case 2 transformation we ended up this. Now we continue to see if case 3 is applicable. So case 3 is, here the parent is red while the case 3 parent expects to be black. So case 3 is not applicable. So we go to case 4, parent is red, the parent of the double black node is red. This is black and these two null nodes are black. All the null nodes are black. So case 4 is applicable. The parent is red in color, the sibling is black, and both the children are black. So then we do a case 4 transformation, which was nothing but change this to red and this to black. And as soon as we do that, this is no more a double black node but just a single null black node. And now this is back to red black tree. Let's make sure that the count of black nodes is same in every path. So 4, 4, 4, 4, 4, 4, 4. So yeah, so this is a red black tree. So as you can see, we did a case 2 transformation and then we changed it into a problem where the sibling was from red, the sibling becomes black in color. And once we did that, we see which of the other cases gets applicable, and we ended up at case 4, which is a terminating case. So we did a case 4 transformation and this is back into red black tree. So next, let's quickly summarize all the cases and then look at the code for red black tree deletion. Summarizing the entire process, first find the node that needs to be deleted by doing a traversal in binary search tree. After you found the node, if it has 2 not null children, then find its in-order successor, which is the smallest element in the right subtree, replace that in-order successor in place of this node that needs to be deleted, and then delete the in-order successor. Either way, you will end up in a place where the node needs to be deleted is either has 0 or 1 child, not null child. If the node that needs to be deleted is red node, then just delete that node, because deleting that node is not going to affect the count of black nodes in every path. If the node that needs to be deleted is black but it has 1 red child, then replace that red child in its place and change the color of the red child to be black, and this again keeps the count of the black node in every path the same. Otherwise, if we have a black node that needs to be deleted with 2 black null leaf nodes, then we have this double black node situation, in which case we have this one of the 6 cases, and then we do that transformation, and then we might have more transformations. So hopefully this helps you understand the entire process of doing deletion in red-black tree. So the time complexity for deletion, as you can guess, is O of log n. So in the next section, let's look at the code for deletion.
The code for delete, it takes the root of the red-black tree, it takes the data that needs to be deleted, and it takes this atomic reference, root reference, which is like a double pointer in C, because the root could be changed and we want to hold the new root in this root reference. So then first we do is our regular binary search and look for the node that needs to be deleted. So if root data is less than data, we go on the right side, otherwise we go on the left side. Once we find that the root that needs to be deleted, we go into this if condition, and then we check, does this root have 0 or 1 not null child? If it does, then we go into this delete one child use case. Otherwise, we find the in-order successor, which is the smallest in the right subtree, and replace root data with the in-order successor data. So root data is gone, but now we have to delete the extra in-order successor data. So we again go into this delete recursive call, and this time we go on the right side of the root and passing in-order successor data. So now let's look at this delete one child method. So in this method, we find the one not null child if it exists. Otherwise, it will be a null null node. And then first we replace the node to be deleted with this child node, basically saying that making the parent of this node to be deleted point to the child and making the child point to this parent. And then once we are done that, then we see if the color of the node to be deleted is black. If it is black, then we check if the color of the right child is, if the color of the child is red. If the color of the child is red, then we just change the color of the child to be black, as we discussed before in the video. Otherwise, we have this double black situation, and we'll start going into this case 1, case 2, and so on. If the node to be deleted's color was red, in that case we have nothing to do, because the deleting a red node doesn't affect the count of the black property, so we are done. So anyways, if we hit a double black situation, then we go into this delete case 1, and we start from case 1. So if the case 1 was, if the double black node that needs to be deleted is root node, so its parent is null, then we just update the root reference and return, because that's a terminal condition and we have to do nothing. Otherwise, we go to case 2, and in case 2 we check if the sibling is red and do some rotations, and since case 2 is not a terminating case, we go into case 3. So if we hit case 2, then we'll do some rotations and go to case 3, and if we don't hit case 2, they will still go into case 3. In case 3, case 3 was again was the one which you used to bubble the problem up. So if it satisfies the property of case 3, then we change the color of the sibling red and then we have just bubbled up the problem at the above level, at the parent level. So all we do is delete, we go back to the delete case 1. This time the double black node will be the parent of the current double black node. And if we don't satisfy case 3, then we just go into case 4. In case 4, if the properties for the case 4 is satisfied, and case 4 is a terminal state, so we do some recoloring and then we just return because we are done. Otherwise, we go into case 5. In case 5, we were doing some recoloring and rotation so that we can prepare it for case 6. And so if we do satisfy the condition for case 5, we will do some rotations and prepare it for case 6. And if we do not satisfy the condition for case 5, we jump directly into case 6. And case 6, if you remember, was doing the rotation and recoloring, and case 6 was also a terminal case. So while we reach case 6, we do some rotations, and then we are done with the red-black deletion, and the red-black tree is back to being a red-black tree. So this is all I have to talk about red-black tree. The link to this code is in the description section of the video. Please like this video, comment on this video, check out my Facebook page, facebook.com/TusharRoy25. Check out my GitHub link, github.com mission peace interview wiki. Thanks again for watching this video.